Hi, this is Nastaninowski. We're doing the homework problems for Chapter 32. So, analysis of algorithm. This is in Corman, Liza, and Rivest. So, Chapter 32 is about string matching. As always, you're supposed to do the problem first. Okay. So, Chapter 32, Section 1, Number 1, is a simple problem. They give you the pattern is equal to 0, 0, 0, 1, and the text is equal to 0, 0, 0, 0, 1, 0, 0, 0, 1, okay, 0, 1, 0, 0, 0, 1. Okay, and let's read the question. One second. Show the comparisons the naive string matcher makes for the pattern, okay, and for this pattern in this text. Okay. The main point of this is there's a lot of repetition. Okay, so here it's going to go as follows. 0 is going to match up with 0. That's very good. Then 0 is going to match up with 0. That's good. 0 is going to match up with 0. That's good. That's no good. Okay, 1 doesn't match up with 0. The main point is the next thing that's going to happen is this is going to match up with this. Okay, so we're not going to move over a whole thing. We're going to try doing this. Then this will match up with this. Then this will match up with this. The main point is we were going along forward here and we had to back up. Okay, because that didn't match. And then finally that matches with that and we're finished. Okay, that totally matches up. So 0, 0, 0, 1, there you have the pattern right there. The main point, you backed up. Good. Keep that in mind when we do the next problem. Okay, so now we're doing 32.1 section 2. Okay, problem 2. So that takes care of that. Number 2 is as follows. Okay, suppose that all characters in the pattern are different. Show how to accelerate naive string matcher to run in time O of n for an n character text. Okay. So it goes as follows. I want you to, we're going to do something different than this. Okay, so we're going to have as follows. The pattern is equal to, let's say, A, B, C, D. That's a pretty simple pattern where every single character is different. That's what they want. Suppose that all the characters in the pattern are different. Now, let's look at the text. Text is equal to A, B, C, let's say S, A, B, C, let's say T, A, B, then A, B, C, D. Okay? Okay? So let's see how this matches up, how we can do this in an accelerated way. So let's go through it. A is going to match up with B. B is going to match up with B. C is going to match up with D. D is not going to match up with S. Okay, so we fail. But what do we know? Okay, since B matched up with B, and we know that these two, every letter on the top here is different, so there's no reason to go try the A with the B, because we know since it matched up well over here, that it's not going to match up. So the first time that an A can show up again is over here. Again, you're looking at it like this. A matched up with A, B matched up with B, C matched up with D matched up with S. But because we know B matched up with B and we know that A is different than B, we don't have to do this again. We don't have to do this again. You don't have to do this again. What we do have to do is A matches up with S. Okay? And we'll see that that's not true. Okay? So let's go further. So then we keep on going. A matches up with A. That's true. B matches up with B. C matches up with C. D matches up with D. No, that fails. Okay, and again, because B is different than A, we don't have to backtrack again. We can just keep on going forward this way. Okay, and so we're going to try A with T, B, which fails, by the way. And by the way, that one fails too. And so we go A with A with B, C with A fails, and then we do A with A, and then finally we get it. But the main point is you can continually go in here because each of these letters are different, so when they match up with something, you can know that you can go forward. Okay, that's fine and dandy, but I would like to write the algorithm for that. And the algorithm is a little bit more complicated because you have to put in more details about it. So I don't want to erase that because we're actually going to need that. So here's the way the algorithm goes. So I wrote it out. It's called naive what's a good word for this? String matching with a pattern, but we want that the pattern should have different with diverse pattern. Oh, that's cute. Diverse pattern. Okay. Anyways, it's just a name, so it doesn't matter what we do it. Okay, and it gets a text and a pattern. Okay, and it starts off the same way as before. Okay, n is equal to t dot length. Okay, I'm assuming you've seen this, and in the third diagram, the regular algorithm in the third edition is page 988. Okay, m is equal to p dot length. Okay, and then what I want to do is I want to find it. Where's the position of the pattern in the text? And so we make a variable called s is equal to 1. Now, in the book's version, it's done with a for loop, a very simple for loop. But here we have to go into little nitty-gritty details to make sure we have to go through 2 loops. And I don't want them to be for loops because I want to advance things. I'm not saying my algorithm's the best. I'm sure everybody's going to put corrections to my algorithms or better versions in the hints below, in the notes below in the YouTube channel. But that's okay. Okay. Do while. Okay, remember that. S is less than. S is less than n minus m. In other words, do this outer loop until you get till the end of the text. Okay, but not really all the way to the end of the text, but the end of the text until there. I could be off by -1 or +1 here. I could have made a mistake. Okay, great. I is equal to 1. Okay, now what I want to do is I want to look at the first position of the pattern and the first position of the text. Shifted over, S. Okay, then the second position of the pattern and the second position shifted over. Okay, and so we do that like this. Okay, I need a little flag. Flag equals true. Okay, and the point is I want to know, did we find it yet? Yes or no? And we can do a little bit more clearer here. Okay, so let's do this. Flag is equal to true. Okay. Do while, it's a little clearer but lighter. Flag is equal to true. That means we found what we're looking for so far. In other words, going further. We're going, now what we're going to do is this inner loop, so this is an outer loop, trying it one by one, and this outer loop, I'm sorry, that's an outer loop, trying every m places, and now we do the inner loop. You can do this, there are better ways of doing this. Do while flag is equal to true, and I is less than m. In other words, we didn't come to the end of the pattern. Okay, and here's the main thing. If P of I, that's the ith position of the pattern, is equal to T of S, okay, if the pattern is equal, if the pattern is equal to the pattern, then increment the I, in other words, go forward in the pattern, also go forward in the text, s is equal to s plus 1, and then stop. Okay? Else, if it's not, then flag, in other words, if these two things are not equal, then set the flag equal to false. Okay? And I have to back up one extra spot. In other words, we always move forward, but I want to back up one extra spot. I'm sure there's a way of fixing this. So this becomes s is equal to s minus 1. Back up 1. Okay? And finally, we're here. If flag equals true, okay, and maybe equal, okay, then print, and just the same thing as was before, just the same thing as what was in the book's version. Pattern occurs with shift S. Okay, and that's it. The main point is how much does this algorithm works? Well, S starts at 1, and S just keeps on incrementing this. You're basically doing this over and over until S gets till n minus m, but it sometimes has to back up. Basically, it's O of n, where n is the length of the text. Okay, so you keep on moving forward. The idea of the algorithm is basically here. You keep on moving forward. You don't have to check back like you did over here and say, oh, maybe the second thing starts, because if all the letters are different, then you can keep on moving. So that's a nice algorithm. Okay, again, I'm sure there are better ways of doing this with for loops, fancier for loops with different steps and things like that. Okay, let's just do this quickly. That's not good. Okay, let's press pause. Okay, the next thing is section 32-3. This is solving the problem using finite automatons. So the first one is a basic, simple thing. We have the pattern AABAB. Pattern is equal to AABAB. Okay, and they want us to write the finite automaton that finds these patterns. I like to do it the way I like to do it. You don't have to give the names to the states, or you can better way of saying it is you can give any name you want to the state. So this is the way I do it, and I try to do it like this in class. Okay, it goes as follows. Okay, along the spine you write the pattern A, B, A, B. Okay. The main innovation is I put what you already have inside the state. So you have nothing in the state here. Here you have an A. Here you have AA. Here you have AAB. Here you have AABA. And here you have the entire pattern. Okay? And now it's easy to write what you're missing. So here, in other words, for the other letters, the alphabet is A comma B. Okay, and so here, if you have a B, you just wait. Here, if you have an A, you go here. If you have a B, you go back and wait. Okay, here, if you have a B, you go here. If you have an A, then you just had AA, and you're going to have another A. Well, you just stay right there and wait. Okay. Here, you have AAB. If you have an A, you go here. If you have a B, then you just had two B's. There's nothing in the pattern with two B's. So you have to go all the way back to there. Okay. And finally here, if you have a B, you go, yeah, it means you got the entire pattern. That's good. But if you have an A, then look what you just had. If you just had an A and you have another A, that means you had two A's, okay, then you go right over here. Okay, and finally, once you find the pattern, you stay right there, A, comma, B, right there. Okay, that takes care of that. But to finish the sentence, construct a string matching automaton for the pattern like this, and its operation on the string AAA. Let's write it. The text is equal to AAA, BAB, AA, BAA, BAB, AAB. Okay. The main point of this finite automaton is you don't have to go back. This is what we just spoke about 2 minutes ago. You don't have to go back. So let's go through it. Okay. So let's go through it. You ready? You need 3 fingers to do this. Let's do it. You ready? A, okay, A, you stay here, then B, A, B. And there you have the pattern right there and there. A, B, A, B. I suspect that they didn't mean to ask it, but anyways, so that was pretty easy. Unless I made a mistake writing it down. Let's go through it. AAA, BAB. Okay. Anyways, so we did that. Okay. The next problem, let's clean this up for a second. Okay. It's just they're trying to be painful, so we're gonna not listen to them. Don't move. Let's read the next problem. It says as follows. Draw a state transition diagram for a string matching automaton for the pattern, and then it gives a giant pattern. Okay? I simply don't have the room, nor do I have the patience to do them all. But I'm going to do the first 5 or 6 letters so we can get it. Ready? Okay, I'll put that there. Ready? Pattern is equal to A, B, A, B, B, A. A, B, A, B, B, A. B, B, A, B, 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 A, B. Okay, that's enough. It goes on for a lot more letters, but I'm not interested in it because we're gonna, it's just not that interesting. So let's erase this so we can get a little bit more room here. We need width of the board because it's a long thing. Okay, and let's do it. Ready? So we have a starting state, and we just write it along the spine. So we have, let's just do it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. I'm going to get bored here. 1, 2, 3, 4, 5, 6. Okay, so we're only going to do 7. So let's do it. Okay, you start off with the empty thing, then you put down an A. So this is a state where you have an A. Then here you have a state AB. Then here you can have a state ABA. Then here you're going to have a state ABAB. And then here you're going to have a state ABA. B, and here you can have a state A, B, B, A. Okay? And even this we won't do. Okay, so let's do this. A, B, A, B, B, A. A, B, A. Okay? The idea is the same, so let's write this down. A, B, A, B, B, A. What you do is you take your piece of paper and you put it lines sideways. Do it a whole long thing. But again, once you get the feel of it, you don't really have to do that. There's no brains to this, so let's do it. Okay, here, if you get a B, you stay here. If you get an A, you go forward. If you have a B, you go forward. If you have an A, well, you just stay right there. Okay, if you have an AB and you have an A, then you go here. If you have an AB and then you have a B, so the last two things you had a BB, so you go back to the beginning because you don't have anything in your pattern. Okay, if you have an ABA and you have a B, you go here. That's good. But if you have an ABA and you have another A, so you should wait for a B. So you should go here. Okay, the way to think of this is an A that gets you here, this is an A that gets you here. So, okay, maybe I made a mistake there. Yeah, I think I'm right. The last two things I have is an AA. Okay, good. You're here. You have a B. You go here. If you have an A, so then you have the last three things you have is ABA. So if you have an A, you go here. Notice this, ABA. That takes you right there. Okay. Finally, here, if you have an A, you go here. If you have a B, then the last three things you have is a B, B, and a B. 3 B's. Okay, which takes you, 3 B's is not what you want. There's nowhere in your pattern with 3 B's. So you go back and you start over waiting for the beginning. Okay? Okay. Here, well, we erased this already. Anyways, it goes on and on like this. So you can go do it if you have a long enough time and patience. Anyways, so that's chapter 32, or the parts that we did of chapter 32. Okay? I hope you enjoy.